Just stop it for a moment and try again. That's right, time is money, and I'm live. Okay, so hopefully now you can see me. Let me know if everything's gone right. Okay, so yeah, what I have for you today is I have a load of kind of common answers from Edexcel paper 1. Now, if you're not Edexcel, then I suggest you stick around anyway, because there'll be common things on loads of different papers. But what I suggest you do is you do what I did to get these common answers, which is to look through loads of past mark schemes. Hi you guys, it's great to see you all. Look through loads of past mark schemes and just look for those explain answers that come up time and time again. So I hope you know what I mean. It's the type of thing that you're going to see in this video, and I'm going to jump straight through it into a minute. Make sure you are subbed up, because I'm going to hopefully do this type of live stream before both the next 2 exams. Okay. I have also suggested videos in the description that you should definitely be checking out. And what I'll do is I'll scroll back up through the chat and I'll look for any questions at the end. So save your questions at the end. Let's go through the common explain answers. I suggest you spend the time tonight not over stressing it, okay, just looking through this list of common answers, trying to memorize them and trying to get those kind of stock key phrases for explain questions that's going to get you marks. So definitely are going to get you marks. So let's cut into the PowerPoint now. I'm not a one for PowerPoint normally, so this is a kind of new thing for me, and I'm just going to go through this. Yeah, great stuff to see people are sharing with their class. It's great to see you all here. I know you're working really, really hard. It's the last little bit now, and then you can have that amazing summer. So here they are then, let's go through them. So this one is often coming up when they're talking about currents. So heating causing resistance. So make sure you mention that the amplitude of the vibrating ions increase, causing the frequency of the collisions to increase. So that's the number of collisions per second to increase. The rate of flow of electrons therefore decreases, so that is using kind of a bit of I-nave as well. That idea V goes down, the drift velocity in I-nave goes down. So EM induction, explaining that. If you spot the questions about EM induction, then you've got to bang on Faraday's law basically. So that means a changing magnetic field, so it's a dN phi. Causes a rate of change of flux linkage. So there's got to be a rate of change. The EMF induced is proportional to a rate of change of flux linkage, is Faraday's law. So that induces an EMF. So there's 1, 2, 3. Those 3 points on the mark scheme, always going to get you marks. If it's you spot that question is about EM induction, get those things in. The next one. Okay, Rutherford. So explaining Rutherford, if that's on your paper 1, then most alpha particles pass through undeflected. Very small number are deflected through an angle greater than 90 degrees. This suggests that there's a charged nucleus, because there's got to be a force on that, and that the nucleus has a very small diameter. And then most of the mass is concentrated in the nucleus. So get those things in. Get those 1, 2, 3, 4 key points there. All those emboldened bits there. Okay, next bit. Spot the Newton's law question. I love to play. I always play whenever I do any physics exam. I always spot the Newton's law question, because it's such a key important thing. And really there's only 2 Newton's laws, 1 and 2 and 3. So the first one is about 0 resultant force, therefore 0 acceleration. Students always make that mistake. They don't say acceleration, they say doesn't move, etc. Okay, and then talking about Newton's second law, a resultant force is proportional to acceleration, not about movement but about acceleration, change in speed or direction. And then Newton's third law is the next part on this. The forces of different types, they act on the different object. Now this actually was this question here is actually for why is it not an example of Newton's third law. Okay, so for Newton's third law, they act on Newton's third law. They have to be the same type. They have to be on different objects. Okay, so the magnitude of the force is the same. So talk about those things. This is an example of a question applying Newton's third law, or discussing whether something is or isn't Newton's third law. But those are the key points in bold you need to talk about. Action reaction pair, or reference Newton 3. If you spot it's about Newton 3, make sure you're saying exactly who is on Newton 3. Okay, moving on. And there is they've got to be always the same line of action, the same time of action, different objects, opposite direction, same magnitude for Newton's third law. So spot the Newton's law question and get those full definitions into Newton's law questions. Energy transfer, okay, always talk about the different stores and then the transfer. So work done is a transfer mechanically by forces. Transfer of energy, increase in the kinetic energy of the thing, say that. Okay, the kinetic store of the object. And once this question was about a cyclist, once the cyclist was at that terminal velocity, all the energy supplied is being transferred into other stores. Okay, get those points into your answer. Okay, moving on. This is in circular motion applied to particle physics. So F equals BQV, or BIL indeed, is equal to F equals mv squared over r. So whenever you recognise centripetal force, then your answer is likely to be about mv squared over r, because that's the equation for centripetal force. Okay, hence the force is always towards the center. State that it's a centripetal force towards the center of the circle, so providing a centripetal acceleration. So that's a change in velocity but not speed, it's motion in a circle. Okay, next one, nuclear stability. Always talk about the energy, the binding energy is equivalent to the mass deficit. That's E equals mc squared. So when nucleons bind together to form a atomic nucleus, okay, so a bit of mass goes missing, and that's the mass deficit. That is the delta M, and that's converted to the delta E in E equals mc squared. So this is creation or annihilation. So all nuclear physics is all about this equation here, creation or annihilation. When something's created, the energy of the cosmic ray is turned into mass or matter by E equals mc squared. And you can do the opposite. Annihilation is matter turning into energy. Okay, next one. Projectiles. So they often ask you to do, obviously, the calculations. I'm not talking so much about calculations, but you could ask them in the Q&A later. But then they'd say, why would this be lower than the actual value? And that's because air resistance acts as a decelerating force. So the initial speed is going to be lower, or the speed during the thing. This is an application. I think this question was about popping a cork out of a bottle, and actually the initial speed was a bit lower because it was corking, because there was actually a resistance from the bottle. I can't remember, or maybe this was the one where they were talking about the bubbles, how far the bubbles went, but it doesn't matter. The point is, when we do projectiles, we ignore air resistance. Okay, next one. Not too many more to go. So terminal velocity one. So this is about a parachute, but it's about applying to any situation. Whenever you've got terminal velocity, you've got this balance between the upwards forces and the lower forces. So this is talking about initially the parachute opens at point B on that graph, upwards force increases, therefore drag is greater than weight, therefore decelerates, okay? And then eventually the drag force balances the weight, they are equal, and this is straight out of mark schemes incidentally, so no acceleration. So really terminal velocity is just a Newton's laws question. I'm sorry, I'm laughing at some of the stuff in the chat there, excited for Q&A coming later. Okay, particle detectors. Neutral particles do not leave a track or ionize. Right, apologies if binding energy comes in paper 2, not a problem. Neutral particles do not leave a track. Okay, in particle detectors they don't leave a track. Then reference to conservation laws to deduce the properties of particles. So those conservation laws are conservation of mass, conservation of energy, there's the obvious ones, conservation of baryon number, lepton number, and charge are the other ones, and strangeness if it's weak interaction. But that's not on Edexcel, that one. We use the tracks to determine the momentum, and the curvature also indicates the sign of the charge. So it's curved one way by Fleming's left-hand rule if it's a positive, and another way if it's a negative. And the radius of the curvature is an indication of the momentum, because it's losing momentum by ionizing particles as it goes through the bubble chamber. Next one, so particle definitions. What is a boson, a baryon, and what is a meson? Well, a meson is always a quark-antiquark pair, so that statement gets you a mark. So, and it always adds up to integer charge, always adds up to 0, 1, or -1, so quark-antiquark pair. Whereas leptons are fundamental particles. So it's definition of these things. Baryons are free quarks. Okay, just defining those things is an common explain question. And last one in this one, collisions. Elastic collisions conserve kinetic energy is the mark that's going loads, and also applying conservation of momentum. So momentum is always conserved, kinetic energy is not always conserved. Right, that is that, everybody. That is me going through that PowerPoint. I hope that was helpful. I'm going to go back across into my normal kind of webcam shout. I hope that was useful. Let me know if that was useful. You appreciate that? That's good. In the description, I've also put the link to this PowerPoint itself, just as a set of PDFs, and I've got the same thing for paper 2. Okay. How was that helpful for you? Let's have a quick look at the chat now, and then I'll come into Q&A. Okay, so this is the chat box, and you're going to get get yourself on air if you are saying anything. Good. All right. Sorry it was a bit late initially. I hope that was helpful. How's your revision going? What kind of things are you focusing on? Let's hear about it just now. Ask any questions. I've got a visualizer. I'll do any bits quickly that I can do justice to. If I think that I won't, then I'll maybe point you in the direction of other videos or something like that. Was it helpful for other things? Great. Very helpful. Appreciate that. That's really good. Thanks. Good to see you all. Good to see loads of people. I now realise how much I don't know. No, it's not dumb. It's not that you don't know this stuff. What it is that you're perhaps trying to explain it without just memorising those kind of key phrases. All those bits in bold in that, and if you watch that back through, all those bits in bold in that is just the kind of stock phrases to make sure you get the marks. Okay. Do we need to know about cloud and bubble chambers in the Edexcel paper? Yeah, but only really those principles. I think in the spec it just says the principles of acceleration and detection. So I have a really good playlist actually. If you go onto my channel and you find the A-level playlist, regardless of what board you're doing, that'd be a really useful thing for you to do. And one of my best playlists is actually the particle physics, because I'm a big fan of particle physics, so it might be worth you checking out that. You just need to know the principles of acceleration is always accelerating through electric fields and using magnetic fields to kind of deflect particles, and principles of detection is you have to pass it through something that it ionizes. That's why you can't detect the neutral particles, and then you can analyze the tracks looking at momentum, looking at charge, and that's about it really. Okay, you want to look at potential dividers quickly, John? Okay. John, Dr. John. I've got a good potential divider video as well, John. So definitely, but I'll just do that quickly. Any predictions for 6 marks? I don't make predictions, YOLO Gamer, because I wouldn't want to be wrong for you guys. Will capacitor discharge graphs come up and equations? Almost certainly they will. I've got a really good video of capacitor discharge. So if you're looking at electric fields playlist on my channel, that's really good. Okay, why are high energies needed? High energies needed to investigate the structure of nucleons. Well, lots of reasons really. The main reason why we need lots of energy when we investigate particles is energy being converted into mass. So lots of energy converts into a little bit of mass. So you need really high energies to make these massive particles that we're interested in. But if you're interested in investigating neutrons, then you're really thinking probably the deep inelastic scattering. So basically a neutron appears to be a fundamental particle. It appears to have no structure at normal kind of collision speeds, low energy collisions, because it acts like a solid sphere. But the highest energies, once you get higher energy, you get inside the neutron and you do what's called deep inelastic scattering. So deep inelastic scattering is what it sounds like. It's deep within the neutron, and it's not elastic, so it doesn't behave like a solid sphere at that point. It's because it has got a structure essentially. So I'm going to do exactly. Arab's got that, to overcome the electrostatic forces. So you need the high energy to get close enough to do the interaction. The only topics that haven't appeared in 2017 or 2018 that might appear this year, not sure, G. I'm sorry. I just don't do that really, because like for me, when I was revising for things, I was just of the opinion that anything could come up. I need to be ready. I definitely went in with my strong and my weak points, that I knew that bits that I was good at and bits that I wasn't. But I'm not going to tell you now that I reckon this and have you spend the whole evening doing something for it that I say, and then find out that it's not the case. Tathat, where do we use root mean square for voltage? Basically all the time. So the 230 volts is the RMS voltage, right? So if you've got AC and you want to work out a current, you might be interested in the peak current, because you might need to know that your fuse isn't going to melt at the peak current, but you're working most of the time as your kind of average current in your AC circuit. So that would be RMS voltage to work out RMS current. I hope that makes sense. What's my opinion on Seneca and Quizlet? They're all, those platforms are great, but some of the resources on there maybe aren't quite the very, very best. So you've just got to be sure that you're doing something. If you look out for something, if you think, hang on a minute, I know that's not quite up to the level, or actually that's a bit too easy, then you're just going to stop there and think, I'm not going to do that. So I'm going to do potential divider. I'm going to do some capacitor maths. Why not? I'll just write these down just in case I forget. And capacitor maths, right? Got good videos on those as well that you can check out afterwards. yeah, you don't need to know baryon numbers and specific strange numbers or anything like that. You just need to be, they're going to give you data and you need to be able to use it. Okay. Yeah, what I'll do, like a couple of these requested videos, I'll put in the main comments. In fact, if you need a video, can you put it in the main comments, and I'll put the link like after this playlist is, after this kind of stream is done. I'm probably going to do about 10 more minutes, and then if after this you put, oh, I need a video on this, then if I've got one, then I'll put one of my videos on it. If I don't have one and I know there's a good one, then I'll put a link to a good one after it as well. Is that okay for you, Sahel? So if you, after this video, just in the main comments, just say, can I have the link for the particle physics playlist? I'll put it in there. Potential dividers coming up in a second, Dragon. You don't need to know how to use the right hand rule. Okay, it's the left hand rule is the motor effect when there's a current and a field, so current and field making a force. You don't need to use the right hand rule, although that is for EM induction. You don't need to work out a direction of that. You just need to know that by Lenz's law, it's opposite to the direction of the change that produced it. Okay, you don't need to use right hand rule. Okay, so you only need to know the left hand rule for Edexcel anyway. It's the same principle for right hand rule. If you did in your spec, then I think that you know it's the same idea. You just line up the two. You line up the motion with the field, and the second finger shows you the direction of the current. But essentially, you just need to know your left hand rule. Two questions there. Derivations are key for paper 1. So I have all the derivations in A-level physics video in the description. Definitely go through that. Which derivations are key? Well, if you look through the spec, you can see, and I say this in this video, you can see which derivations are going to come up in paper 1. So do that. How should you structure 6-mark questions is also, I did a longer written questions live feed last year, which I think is one of the best live feeds I did last year, to be honest, so I would definitely check out that. And really the point I made repeatedly was kind of whatever you do, you just make sure you cover everything in the question. The structure is not as important as making sure you cover everything in the question, and then you sorry, just laughing again. You cover everything in the question and make sure you link your points together. Okay, that's not doesn't mean like we're looking out for words like however or meanwhile or any nonsense like that, but just basically this thing causes this thing, and then that happens because of that thing. So you just link them all together. If you just write them as bullet points, then you wouldn't get the linking marks. Okay, yeah, I hope it's useful for all boys. Yeah, I can't sit the exams for you dudes, yeah. Alright, should we go into the visualizer then? Let's check that's alright first. Yeah, there we go. And I'm going to give you the full nice Lego gorilla. So you know who gave me the Lego gorilla? That was from himself, Lord Matheson. Okay, so we're going to do potential dividers first, everybody. Okay, so potential dividers for me are quite straightforward, but I understand why people get them. They find them tricky. They always look like this. Okay. With this is being the 0 voltage down here, and it's just two resistors in series essentially. That's all it is. And this is your input voltage. Let's say 12 volts. Have I got my calculator with me? Yes, I do. You know it. You know what calculator I've got at home. Wow, that is the class whiz. That's the FX991EX. That is the beauty. I hope you've all got your calculators ready. So you basically then you've got two resistances. R1 and R2, I don't know why I put R1 down there. Okay, and it's normally, this is the output one at the bottom in the circuit, but it's probably not going to be drawn out exactly like this. And you just need to work out what V out is. Okay, and it's just a case of sharing out this voltage in this ratio. So let's put some numbers on it. Let's make it sort of reasonably easy for now. So I'll just call this one 10 ohms and call this one 30 ohms, right? So that's a ratio 1 to 3. Okay, and I just do this like sharing out sweets between your friends, literally as simple as that. So 1 to 3 means there's 4 parts, so 12 over 4 is what 1 part is worth. And it sounds silly, but in an exam I literally do that sum in my calculator, because I know that you will know straight away that's 3, but like it saves my brain power for actual difficult things. And if I make a mistake there, then what a silly way to lose a few marks, right? So this is worth 3 volts. So, well, okay, I've got to put 1 share over there and 2 share about there. So literally, this is just 3 volts. So it's just about sharing out things. Now, I think the difficult thing is about spotting the potential divider question. So really, they keep asking you about potential dividers because people seem to find them tricky, right? But if you spot it's a potential divider, then yeah, exactly, Lerox. You just spot the potential divider question and you share it out like you're sharing out a bag of sweets and your friends, right? Okay. You don't need, Kareem, to know the transformer equation, but you can definitely apply it. Okay, the transformer equation is just a quick question there. So is N1 over N2 is equal to V1 over V2, which is just basically saying the ratio of the number of turns is equal to the ratio of the number of volts. The voltage input over the voltage output is the same as the input turns over the output turns. And there's loads of physics which is about ratios, and I think they put it in because for some reason it makes it harder for you guys, but you shouldn't let it make it hard for you. Really, when we're talking about ratios, and ratios can be expressed like this, or they can be expressed as fractions or percentages or anything like that. So just don't be afraid. If it asks you for the ratio of one thing over another, then actually it's just work out one thing and work out another thing, or it's probably going to be something like put the equation for one thing over the equation for the other thing, cancel what you can cancel, and then you've got the ratio. Okay, so it's a little bit like those tricky what's the proportional change. You know, if I double this thing, what's the change in this thing? And you just think to yourself, well, all the other things are fixed and you've only changed one thing, so you're just working like that. So ratios are big deals, but they're pretty straightforward, really. Right, capacitor maths then. Really, this is just another exponential decay. So it could be V, what would it be? Minus T over RC. Okay, and these are in your equation sheet. It could be current, and it could be charge, right? So that's all it is. They're exactly the same thing. And basically, whenever you discharge a capacitor, then you get a graph that looks like this, okay, which is exponential. You know it's exponential because the variable is the exponent. So whenever the variable is the indice of a fixed number, it's exponential. It doesn't necessarily have to be the exponential number, but that's the one that we use. And then to take that down into a y equals mx plus c, you just log both sides, right? So you do ln v equals ln v naught minus T over RC. And then you have, when you plot ln v on your y-axis, you have a graph where the gradient is 1 over or minus 1 over RC. Okay, because you can hopefully see, and then you can hopefully see this is y, this is the intercept c, this is minus mx. So 1 over RC is m and x is t. Okay, so I hope that's okay. Now, if you're not sure about this bit I've just done there, then go ahead and watch some videos about exponential decay, because so again, if you want a video, then after this video is dropped, then in the comments, the proper comments for this, not the chat, then put, can I have this video please, and I'll put a link for it if I've got one, or I'll find one of A-Level Physics Online or somebody else that I think is good. I'll find a good quality video for you anyway. Does that make sense? I hope that makes sense. So basically the rate of decay of a capacitor is caused by the product of R and C, which is what you call the time constant for this decay. All decay equations, all exponential decays are the same basic thing. Okay, I'm probably gonna leave this now, if that's all right. I hope that's been useful to you. You can have a little look at my Lego Gorilla again, and any kind of quick last little points. What's the point of RC? RC is what you call a time constant. Yeah, exactly. And John, the time constant equals 37%, because e to the power of 1 is, yeah, let's do that in the old class whiz. E power 1 is 2.71. It's e to the power minus 1, isn't it? Thank you very much, John. E to the power minus 1 is 0.37, basically. Okay, which means 37%. So when RC equals 1, then you've got e to the power minus 1, and hey presto, that's a useful number to remember. So it is a useful number. If I go back to this thing, so it is a useful number. So that 37%, this value here is RC, okay, or is it? That's 37% over there, isn't it? Okay, and this value here, this is the half-life of the thing, is the point at which V over V naught equals a half. Yeah, in other words, V naught is twice what that is, and that's where half-life was all about. Okay, So I hope they're useful little rules of thumb for you. Okay, I'll go back to the chat. Why, thank you, Mr. No One Knows 2008. Mr. No One Knows. That's a DC equation for the capacitor. Everything is changing. Okay, yeah. So you're talking about when I've got an AC on a capacitor, yeah, but it's still charge and discharge basically. So you charge it and you discharge. You don't have to do the maths for the charging, luckily, which is useful, isn't it? Okay. Yeah, you don't need to you don't need to be able to use the charging. You need to know the shape of it, I think, which is just an inverse exponential curve, basically. Yeah, okay, hope it's alright. Hope it's been really useful for you. I'm going to say ta-ra now. As I say, tonight, don't overstress it. You got any other requests, then put them down in the main things. Okay, yeah, that's good to see you kind of helping people out. Tafat says, what about V out equals V in? Yeah, well, that basically, that equation, Tafat, that you've just quoted there, if you look back at the chat there, is just what I did, but in kind of an equation. And if you want to memorize that equation and use that for your potential divider, that's fine. But I think it's far easier to be confident in my own maths and think to myself, yeah, I can solve a ratio. I can share out this. Voltage in this ratio. I can do that. Like, even if it's a really tricky set of numbers or whatever, I can do that. I can just figure out what one part is worth and so on and so forth. And it's never let me down so far. So if you want to memorize that equation, that's fine. But if it's a tricky one, then you might not be able to do that. Waves and optics, tricky questions. Waves aren't, they're on paper 2 for Edexcel, so I'm not going to look at those just now. But there are some tricky ones in those. I would definitely go through the Finland's equation, and yeah, if you look into the playlist that I've got for Edexcel, there are some tricky questions for waves and optics there in paper 2 as well. So I would definitely look down in there, right at the very bottom of the description, and there's all the kind of exam playlists. And I definitely recommend giving those a watch, because they are going to have some tricky questions like that can help you by going through those just now, Robert. I hope that helps. All right. Yeah. Okay, that's been awesome. I hope it's been useful for you. As I say, next thing to do now, don't overstress things tonight, into the description, and just kind of do some leisurely kind of watching those. Rewatch that first bit where I went through that PowerPoint. Get that PowerPoint for yourself on your phone if you want, so you can just flick through it, in the hours leading up to the exams. Don't overstress it just now. You're not going to magically learn everything. Go through those derivations, and I think derivations are a good kind of warm-up to get you feeling algebraic and get you kind of, ready to do that manipulation at that high level in the exams. All right. So have a good night. Get yourself an early night's sleep tonight. And have yourself a good breakfast and do all the things that you know is good practice for exams, and you'll be absolutely fine. You don't need luck. Okay, I'm not going to say luck to you, because if you're here, you're probably being well prepared. You've probably been working hard on it, and you won't need luck. If you're prepared, you don't need luck. All right, cheers now.